Welcome to today's session. In this problem, we'll tackle an intriguing challenge titled Minimum Number of Days to Disconnect Island. This problem involves analyzing a binary grid and determining the minimum number of days required to disconnect an island. Let's dive in and explore the solution together. In this problem, you are given an nxn binary grid called grid, where each cell is either 0, representing water, or 1, representing land. The goal is to work with what is called an island, which is defined as a maximal group of 1s that are connected in 4 cardinal directions: up, down, left, or right. The grid is considered connected if you can traverse between any two 1s by moving only through other 1s. The challenge is to determine the minimum number of days required to disconnect the grid so that no single island exists anymore. Each day, you are allowed to convert one land cell, or 1, into water, represented by 0. If the grid starts off already disconnected, you simply return 0 as no changes are needed. The input consists of a 2D list of integers, and the output is an integer that represents the minimum number of days required to achieve this disconnection. To understand this problem better, let's look at the first example. The input grid is a 3x3 matrix that looks like this: 0, 1, 0, 1, 1, 1, 0, 1, 0. The output here is 2. Initially, the grid is a single connected island because all the 1s are accessible from one another. On the first day, we change the cell at position grid 1, 1, the center of the island, from 1 to 0. This breaks the central connection, but the remaining 1s are still all connected, meaning the grid is not yet fully disconnected. So, we need to continue modifying the grid further. After the first modification, the grid remains connected, so we proceed to the second day. On this day, we change the cell at position grid 0, 1, the top central land cell, from 1 to 0. Now the grid is no longer a single connected island. Instead, it is broken into multiple smaller regions of 1s that are no longer reachable from each other. At this point, the grid is considered disconnected. Therefore, the minimum number of days required to disconnect the grid in this example is 2. Now let's explore another example for further clarity. In the second example, the input grid is a 2x2 matrix, 1, 1, 1, 1. The output in this case is 1. Initially, the grid is one large connected island, where all the 1s are accessible from each other. On the first day, we change the cell at position grid 0, 0, the top left land cell, from 1 to 0. After this modification, the grid becomes disconnected into two separate regions. Since this was achieved after only one modification, the minimum number of days required in this case is 1. Let's look at one final example to explore a different scenario. In the third example, the grid is given as 1, 0, 0, 1. The output here is 0. This is because the grid starts off already disconnected. The 1s are isolated and cannot be reached from one another, so no modifications are necessary to disconnect the grid. Lastly, let's consider the constraints for this problem. The grid is always a square with dimensions nxn, where n is between 2 and 30. Each cell in the grid is either 0 or 1. Some edge cases to think about include grids that are already disconnected, grids with the smallest possible size of n equals 2, and very large grids with all cells as land, which would require multiple steps to disconnect. These constraints and examples should help you understand the problem and edge cases thoroughly. To solve this problem, we first need to understand its core requirements. The goal is to determine the minimum number of days required to disconnect an island within a binary grid. Here, an island is defined as a group of ones that are connected in 4 directions, and to disconnect it means splitting it into multiple disjoint parts or eliminating all land entirely. The problem can be broken into 2 main steps. First, we need to check if the island is already disconnected. This can be done using graph traversal techniques like DFS or BFS. Second, we simulate the removal of land cells to see how the structure of the island changes. The objective is to determine the smallest number of land cells that need to be converted to water to achieve disconnection. This sets the foundation for our approach to solving the problem efficiently. One possible approach to solving this is through brute force. The intuition here is straightforward. We can try removing each land cell, one by one, and then check if the island becomes disconnected. The process involves 3 main steps. First, we check if the island is already disconnected using a DFS or BFS traversal. If it's not, we iterate over all land cells. For each cell, we temporarily change it to water and test whether this results in disconnection. If removing one cell isn't enough, we then extend the process to pairs of cells, removing 2 at a time and repeating the check. While simple to understand, this approach has a significant computational cost. Evaluating whether the island is disconnected takes O, n superscript 2, and since we simulate the removal of up to k land cells, the overall complexity becomes O, k asterisk n superscript 2. This makes it impractical for larger grids, as the number of checks grows rapidly. To address the inefficiencies of brute force, we can use an optimized approach based on key observations from graph theory. First, if the island is initially disconnected, the result is 0 days. Second, if removing a single land cell disconnects the island, we return 1. Finally, if one cell isn't sufficient, we check pairs of cells, knowing that at most 2 removals are needed for disconnection in most cases. This insight significantly reduces unnecessary checks. The steps include verifying the initial state, simulating the removal of each individual cell, and stopping early if a solution is found. If no single cell works, we test pairs of cells and return 2 if any pair succeeds. In rare edge cases for small grids, the answer may be 3. While the worst case complexity is O, k superscript 2 asterisk n superscript 2, the use of early stopping and systematic evaluation makes this approach much faster in practice. This strategy is chosen because it balances efficiency and correctness, leveraging graph theory to minimize redundant operations while systematically addressing all possible scenarios. It avoids the inefficiency of brute force while remaining clear and reliable, making it the best fit for this problem. To solve the problem, we need to figure out the minimum number of days required to disconnect an island represented as a binary grid. An island here is defined as a group of land cells, or ones, that are connected either vertically or horizontally. Disconnecting the island means turning one or more of these land cells into water, or zeros, so that the group is no longer a single connected component. To approach this, we start by defining a helper function called is_connected grid. This function determines whether the island is still connected by performing a depth-first search, DFS, or breadth-first search, BFS. Starting from any land cell, it visits all reachable land cells. If all ones in the grid can be visited, the island is considered connected. If not, it is disconnected. This function takes the grid as input and returns a Boolean value indicating the connectivity of the island. Another important helper function is count_land_cells, grid, which counts the total number of land cells in the grid. This count provides an upper limit on the number of cells we might need to remove, helping us optimize the algorithm. Once these helper functions are in place, we start by checking some trivial cases. First, if is_connected grid returns false initially, the island is already disconnected, so no operations are needed, and we can immediately return 0. Next, if the island consists of only one land cell, removing that single cell will disconnect it. In this case, we return 1. For non-trivial grids, we simulate the removal of each land cell to determine if it disconnects the island. For each cell, we temporarily set it to 0, check connectivity using is_connected grid, and record the result if the island becomes disconnected. After the check, we restore the cell back to 1 to preserve the original grid state and ensure each test is independent. Now, if removing a single land cell is not sufficient to disconnect the island, we extend our simulation to consider the removal of 2 cells at a time. For this, we iterate over all possible pairs of land cells. For each pair, we temporarily set both cells to 0 and use is_connected grid to check if the island becomes disconnected. If we find such a pair, we record the day as 2 and stop further checks. As before, we restore both cells back to their original state to ensure the grid remains consistent for subsequent checks. Finally, if no combination of 1 or 2 cells succeeds in disconnecting the island, the problem guarantees that it would take at most 2 days to disconnect. This means we can safely return 2 as the worst-case result, ensuring the algorithm always completes within the specified constraints. The key insights here are that an island is considered disconnected if there is no path between any 2 remaining land cells, and that backtracking is essential for simulating cell removals independently. By restoring the grid after each test, we ensure no unintended changes affect subsequent operations. Additionally, the problem guarantees that disconnecting the island requires removing no more than 2 cells, so testing up to 2 cells is sufficient. The data structures we use include a 2D array to represent the grid, where each cell is either land or water, and a set to track visited cells during DFS or BFS traversal. We also use a queue or stack for efficient grid traversal. As for complexity, the connectivity check through DFS or BFS takes O and *M, where N and M are the grid dimensions. Simulating single-cell removals involves O and *M checks for each land cell, and for 2-cell removals, the complexity is O n squared *M squared, in the worst case. However, due to the problem's constraints, where the grid size is limited to 30 by 30, the algorithm remains computationally feasible. To solve the problem of determining the minimum number of days required to disconnect an island, we begin by defining a function called is_connected. This function checks whether the grid representing the island is still connected. To do this, we initialize a visited matrix to keep track of which cells have already been explored. Next, we iterate through all the cells in the grid to find a land cell, represented by the value 1. Once we find such a cell, we use a breadth-first search, or BFS, to traverse all connected land cells. During the BFS, we maintain a queue to explore neighboring cells and ensure that we don't revisit cells by marking them in the visited matrix. We also count the number of land cells that we visit. If the total number of visited land cells is not equal to the total land cells in the grid, it means the island has been disconnected. Otherwise, the grid remains connected. If no land cells are found, the function returns true, meaning the island is already disconnected. Next, we define the remove_land function, which simulates removing each land cell one by one to check if we can disconnect the island. For each cell in the grid, if it's a land cell, we temporarily set its value to 0 to represent water and check the connectivity of the grid using the is_connected function. If this operation results in the island becoming disconnected, we restore the cell's value to 1 and return true, indicating that removing this land cell is sufficient. If not, we restore the cell's value and continue the process. Now, in the main function, we calculate the grid dimensions, define the directions for BFS, and compute the total number of land cells. If the island is already disconnected, we return 0. If removing one land cell is enough, we return 1. Otherwise, the only remaining possibility is that at least 2 land cells must be removed, so we return 2 as the result. Here, we begin implementing the solution in Java by first defining the structure of our program. We start with the min_deis method, which takes a 2D grid representing the island as input. The grid is composed of 1s, which represent land, and 0s, which represent water. To begin, we calculate the number of rows and columns in the grid, and initialize total land to count the total number of land cells. We also define the directions array, which will help us navigate in 4 possible directions: up, down, left, and right. Next, we iterate through the grid to calculate the total number of land cells by summing up the values of all the grid elements. If the function isConnected determines that the island is already disconnected, meaning there's no single connected landmass, we immediately return 0, as no further action is needed. Otherwise, we simulate removing one land cell at a time to check if it disconnects the island. For each land cell, we temporarily set it to 0, and if this leads to disconnection, we restore the cell and return 1, indicating that 1 removal is sufficient. If removing one land cell is not enough to disconnect the island, the program will then conclude that at least 2 cells must be removed. This is because the island is highly connected, and removing just one cell cannot sever all paths between land regions. At the heart of the solution is the isConnected helper function, which determines whether the grid still contains a single connected landmass. This function uses a breadth-first search (BFS) approach to count the number of reachable land cells from an arbitrary starting point. If the number of reachable land cells does not match total land, it indicates disconnection. The visited array ensures that each cell is processed only once during BFS, and the loop iterates over all cells to find the first land cell to start the search. If no land cells are found, the function returns true, as the grid is effectively disconnected. The implementation of the BFS method is shown here. This function performs a breadth-first search to traverse all connected land cells starting from the given coordinates. We use a queue to manage the cells to be explored, initializing it with the starting cell and marking it as visited. The count variable keeps track of the number of land cells visited during the traversal. As we dequeue each cell, we explore its neighbors in all four directions using the directions array. For each valid neighbor, meaning it is within bounds, not visited, and is a land cell, we mark it as visited and add it to the queue. The BFS continues until the queue is empty, at which point the count is returned. This count represents the size of the connected landmass starting from the initial cell, which is crucial for determining if the grid is still connected after removing a cell. Here, we start with a simple 2x2 grid where the land cells are already disconnected. The grid contains two land cells, represented by the value 1, and two water cells, represented by 0. The algorithm begins by initializing the number of rows and columns to 2, and it defines the possible movement directions for traversing the grid. It calculates that there are two land cells in total. Next, it performs the first connectivity check using the is_connected function. Since the land cells are already disconnected, the function immediately returns true, meaning no further action is needed. As a result, the algorithm concludes that 0 days are required to disconnect the island, and the output is 0. This grid is a bit more complex as it contains 3 connected land cells. The algorithm starts by initializing the grid dimensions, movement directions, and the total number of land cells, which is 3 in this case. During the first connectivity check using BFS, it starts at the top left cell, visiting its neighbors and confirming that all land cells are connected. The is_connected function therefore returns false, indicating that the grid is still fully connected. Now, the algorithm systematically removes each land cell one by one to test if the grid becomes disconnected. For example, when the top left cell, 0, 0, is removed, the resulting grid is checked again for connectivity. This time, the BFS traversal shows that the grid is disconnected, so the remove_land function returns true. With just one removal, the island becomes disconnected, and the algorithm determines that the minimum number of days required is 1. From the previous execution, we see that the grid becomes disconnected after removing just one land cell. Therefore, the algorithm concludes that the final output for this example is 1. This demonstrates that in certain cases, removing a single strategically located land cell can be enough to disconnect the grid entirely. Now, we consider a larger 3x3 grid where all cells are land. The algorithm begins by initializing the grid dimensions, movement directions, and the total number of land cells, which is 9. During the first connectivity check using BFS, it verifies that all land cells are connected, so is_connected returns false. The algorithm then tests the removal of each individual land cell to check if the grid becomes disconnected. For any single removal, such as removing the top left cell, 0, 0, the grid remains connected, as the BFS traversal can still visit all remaining land cells. This means that removing just one cell is insufficient, and the remove_land function returns false for all single cell removals. To disconnect the grid, at least 2 land cells must be removed. For instance, removing the top left cell, 0, 0, and a central cell such as 1, 1, successfully disconnects the grid. The algorithm concludes that 2 removals are necessary, and the final output for this example is 2. To understand the time complexity of our solution, we can break it down into distinct parts. First, consider the is_connected function. This function uses a breadth-first search, or BFS, to determine if the grid remains connected after a modification. In the worst case, the grid is completely filled with land cells, meaning every cell has to be visited exactly once during the traversal. Since each cell has up to 4 neighbors to check, the overall time complexity of this function is O, rows * calls. Next, we have the remove_land function. Here, we iterate through all the cells in the grid, attempting to remove each land cell one by one. For each removal, the is_connected function is called to verify connectivity, leading to a time complexity of O, total_land * rows * calls. Since the number of land cells, total_land, is always less than or equal to the total number of cells in the grid, this simplifies to O, rows * calls, *2, in the worst case for remove_land. Now, let's put the pieces together to analyze the overall execution. The algorithm begins by running is_connected, to check if the grid is already disconnected, which takes O rows asterisk calls. If the grid is still connected, it proceeds to call remove_land, which, as we've seen, has a worst-case complexity of O rows asterisk calls, caret 2. Finally, the step of returning 2 when no solution is found within 1 day is a constant time operation, O1. Therefore, the total time complexity of the algorithm is dominated by the remove_land function, resulting in O rows asterisk calls, caret 2. Shifting to space complexity, the grid itself occupies O rows asterisk calls memory. Additionally, the is_connected function requires a visited matrix, which also takes O rows asterisk calls space. The BFS queue, used during traversal, can hold up to all land cells, which is proportional to the total number of cells in the grid. This means the queue also requires O rows asterisk calls space in the worst case. In addition to the grid, visited matrix, and BFS queue, there are a few auxiliary variables like loop counters and direction arrays, but these contribute only a constant amount of space. Combining all these components, the overall space complexity of the algorithm is O rows asterisk calls, as the grid and BFS related structures dominate the memory usage. Let's now examine the best, average, and worst case scenarios. In the best case, the grid is already disconnected, for example, if there are no land cells or if all land cells are isolated. Here, the algorithm only needs to run is_connected once, with a time complexity of O rows asterisk calls. The average case occurs when the grid is connected, but removing a single land cell is sufficient to disconnect it. While the algorithm does invoke remove_land, it terminates early upon finding the solution, leading to an average case complexity of O rows asterisk calls, caret 2. Finally, in the worst case, disconnecting the grid requires removing at least 2 land cells. This means the algorithm tests all possible single-cell removals, exhausting the remove_land function's full complexity of O rows asterisk calls, caret 2. To highlight the efficiency of the optimized solution, let's compare it to a naive approach. A straightforward but inefficient method would involve testing all combinations of 1 or 2 land cell removals to check connectivity. For a grid with rows asterisk calls cells, testing all single cell removals requires O rows asterisk calls, and testing all pairs of removals involves O rows asterisk calls, caret 2. Each test includes an is_connected call, which takes O rows asterisk calls. This results in an overall time complexity of O rows asterisk calls, caret 3, for the naive approach. In contrast, the optimized solution avoids unnecessary pairwise testing by leveraging early termination and systematically verifying connectivity. By focusing on each land cell removal sequentially, it reduces the time complexity to O rows asterisk calls, caret 2. As a result, the final complexities for the optimized solution are O rows asterisk calls, caret 2, for time and O rows asterisk calls, for space. When tackling this problem, there are several common mistakes to watch out for. First, not checking if the island is already disconnected at the start can lead to incorrect results. If the grid is initially disconnected, the answer is immediately 0, so always verify this before proceeding. Next, incorrect boundary handling can be an issue, particularly in grids with only 1 row or 1 column. These edge cases often trigger out-of-bounds errors or flawed neighbor calculations if not addressed properly. Lastly, inefficient DFS or BFS implementations can significantly slow down your solution. If you recompute connectivity from scratch for every cell removal, the time complexity can balloon to O n to the power of 4 for an nxn grid, which is impractical for larger inputs. Optimizing this step is crucial for solving the problem efficiently. Another common mistake is ignoring the possibility of multiple islands. It's easy to assume there's only one island in the grid, but that's not always the case. Removing a cell might disconnect one island while leaving others intact, so your logic needs to account for this. Additionally, misunderstanding the problem's requirement for 4-directional connectivity can lead to errors. Only up, down, left, and right neighbors count as connected. Diagonal relationships are not valid. This is a critical distinction to keep in mind as you design your solution. From an interview perspective, this problem highlights several important concepts. First, it's a variation of the classic count islands problem, where DFS or BFS is used to explore connectivity. Being comfortable with these techniques is key. Optimization is another major focus. Brute force methods with n to the power of 4 complexity are too slow for large grids, so methods like union find or adjacency lists become essential. You should also pay attention to edge cases, such as grids with no islands, multiple disjoint islands, or minimal dimensions like 1 by 1 or 1xn. Finally, if you find yourself stuck during an interview, clearly explain the brute force approach and outline potential optimizations. This demonstrates both your understanding of the problem and your problem-solving skills. To deepen your understanding of this problem, it's helpful to explore related problems. For example, problem number 200, number of islands, asks you to count islands in a grid using DFS or BFS. Problem number 463, island perimeter, focuses on calculating the perimeter of an island within a grid. Problem number 947, most stones removed with same row or column, involves connectivity concepts and union find techniques. Lastly, problem number 1254, number of closed islands, challenges you to count islands completely surrounded by water. These problems share similar themes and can strengthen your grasp of grid-based algorithms and connectivity logic. Finally, let's discuss alternative approaches to solving this problem. Union find, or disjoint set union, is a powerful method for dynamically tracking connectivity. It's more efficient for large grids, but it does come with added complexity and space requirements. On the other hand, DFS or BFS with pruning can be simpler to implement, though it may still suffer from inefficiencies on larger grids. Pruning techniques can help reduce redundant calculations, improving performance over brute force. Another option is matrix transformation simulation, which can be a helpful visualization tool but is often computationally expensive. The key to optimizing your solution is to avoid recalculating connectivity from scratch for every cell. Instead, pre-compute the island structure and use efficient algorithms like union find or adjacency matrix updates to dynamically track changes. This approach can save significant time and make your solution scalable for larger inputs. Great work! To summarize, we explored how to determine the minimum number of days to disconnect an island using strategic algorithms. Key takeaways included the importance of graph theory and grid manipulation techniques. Stay curious, keep practicing, and don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!